Hello everyone. Today we are doing definite integrals.
Welcome everybody! For the first time ever, we are doing mathematics.
All right, before we get into the meat of today's lecture, I thought it would be good. Sorry about that, my sister is in the room. But anyway, before we get into the meat of today's lecture, I'm going to give you just a little bit of work. So the antiderivative. So remember, going backwards, instead of taking the derivative, we're taking the antiderivative of f of x equal to x to the n, where n is not equal to -1. So n can be anything else, but if n is a -1, it is not this. And then again, we're going backwards here. And so we will add 1. So you're going to add 1 to the power, and then you're going to divide the constant out front by that new power. So this is the new antiderivative, as long as n does not equal -1. For example, let's say that f of x is equal to x to the third power. Then the antiderivative would be x to the fourth power, and then you divide the constant out by 4. All right, let's look at another example. All right, so this example is f of x is equal to 14x to the 6th. So I'm bleeding over into here, but oh well. All right, so 14x to the 6th, and so your new power is to the 7th, and then you're going to divide 14 by 7. And so the antiderivative of 14x to the 6th is 2x to the 7th. So today's lecture is more on the properties of definite integrals, and if you noticed, definite is within parentheses because these properties apply also to indefinite integrals. The first 3 properties we're going to focus on are these. So the first property is the antiderivative, or the definite integral of a constant. So c is a number, it's a constant, and so if you are taking the integral of a constant, then the answer is going to be, or the antiderivative is going to be c times b minus a. For example of number 1, let's go over here. And let's look at an example. I'm going to make this a little bit thinner so I can write. So for example, let's look at the integral from 1 to 3 of 7 dx. So remember, what this means is you are looking at the area under the curve of 7. So f of x is equal to 7. And then we're looking at the area from 1 to 3. And so this is 2. And so we're looking at this guy right here. And so this is a rectangle of height 7. And again, this is not drawn to scale, but of height 7 and width of 3 minus 1. And so the area is going to be equal to 7 times the width of 3 minus 1, which is the same thing. Here, you get 14. You get 14. And again, 7 is acting like our C, and 3 minus 1 is our B, 1 is our A, and 7 is our C in the example of the rule. Now let's look at an example of the property of number 2. So let's move on over and get some space. So here is an example of 2. So let's look at the integral from 1 to 16 of x, and the integral from 1 to 16 of x cubed dx. You're just going to have to trust me for right now. You could calculate this on your own using the Riemann sum definition of a definite integral if you want, or using the fundamental theorem of calculus if you understand that. But we are going to end up with 1/27 0.5. Whereas the definite integral from 1 to 16 of x cubed dx is 16,383.8. Therefore, if we were to take the integral from 1 to 16 of x cubed minus x dx, then this is the same thing as the integral from 1 to 16 of x cubed dx minus the integral from 1 to 16 of x dx, which is equal to that 16,383.8 minus 127.5, which is equal to 16,256.3. So let's look at this last property. So this is combining really 1 and 2 in some ways, where if you have a constant out front in front of your function, or the way to think of this is you have a coefficient, then you can pull out that coefficient outside of your definite integral. So for example, let's go in here and let's look at, let's just stick with this x example from 1 to 16. But now we are going to multiply by 2. So if we have the integral from 1 to 16 of 2x dx, then that is going to be equal to pulling out that 2 out front of 1 to 16 of x dx. And so we already know what that is, so it'll be 2 times the integral from 1 to 16 of x dx is 127.5. And so overall, our answer will be 255. Let's look at the next set of properties of definite integrals. Now these examples, we're going to go a little bit more into the idea of the Riemann sum definition of an integral. So if we look at this first one, so property number 4, if you look at this, you have the integral from b to a of f of x dx is equal to negative the integral from a to b. So we switched our limits of integration. We went from b to a to b. So let's look at this real quick. If we were to draw, so I'm going to zoom in and pull this up so that I can get in here. So example, if we were to draw, let's just think about a constant. So if we're going from 1 to 3 at 7, so this was the example from the very, very first property. The integral from 1 to 3 of 7 dx, if you remember, was 7 times 3 minus 1. Because if we were looking at this, you were going in this direction. You go from bottom to top. And so you're integrating from 1 to 3, which means you have a height of 7 and a width of 3 minus 1. Now let's look at going the other way. So if we were to go, let's do the same thing, but now we're going to go from 3 to 1. So if we take the integral from 3 to 1 of 7 dx, then you're now going this direction. So you're going backwards. You're going in the negative direction. So your height is positive, but your width is negative because you have a negative direction associated with that. And then just to give you an idea, this is going to be 7 times 1 minus 3. So here, with the original from 1 to 3, it's 14, but here it is negative 14. So whenever we are doing definite integrals, they are areas under the curve, but there is a sense of direction with these. So at the end of the lecture on Friday, we discussed how things below the x-axis have a negative area because your height is negative. So now we're going to emphasize on the fact that the direction left and right have a positive and negative implication. And the only way you know which direction you're going is the order that you are writing these limits of integration. So here you're going from 1 to 3, so you are going in the positive right direction. But here you're going from 3 to 1, so you're going negatively to the left. And so this is going to change how you view taking the area of a rectangle. So you're still going to have a positive height, but now you have a negative width. So a positive height times a negative width gives you a negative area. So we just need to pay attention to the direction you are going for these problems. So let's look at the next example. So this one's pretty straightforward. And so if we're looking at this guy, we have the integral of f of x dx, but we're starting at a and we're ending at a, which means that we have no width. And so let's write that real quick. We have no width. So the area of, oh, I didn't even write what that was. So let's go here. So this is equal to 0. So if you are taking the antiderivative, the definite integral of f of x from like 6 to 6. So let me get this down. So like this. So let's go from 6 to 6 of natural log of x dx. Again, we don't know how to take the antiderivative of natural log of x yet, but it doesn't matter because our width is nothing. And so your area under natural log of x is still 0. So it doesn't matter here. Now let's look at our last example here, number 6. So we have the integral from a to c of f of x dx. We can split that up into the integral from a to b of f of x dx plus the integral from b to c of f of x dx. So let's zoom in, and I'm going to draw you a picture of what's going on here. And so example. So if we have like an example here, bloop-a-doo. So here is our f of x, and here is our a, and here is our c. If we were taking the definite integral from here to here, from a to c of this function, it would be very natural to want to split it up at b. We'd want to split it up at b, which for our example is at 0. So we would take this negative area, and then we would take this positive area. And so it'd be natural to split it up in such a way. In general, this is a very, very useful tool to use, especially when you're doing things like absolute value. So we're looking at the absolute value, the integral of the absolute value from -2 to 3. So if we're looking at this guy, if you remember, we have that, let me go down a little bit. So if we're looking at this, then we have something that looks like this. Actually, it looks almost exactly like this. So we're going from -2 to 3. It would make sense to split it up at 0. Again, you don't have to split them at 0. You can just split them in any way that makes sense. And so if we're looking at this, the absolute value from -2 to 0 of the absolute value of x dx plus from 0 to 3 of the absolute value of x dx. And if we look at this, we can see that this guy has, it's the size of a triangle. And so the area of a triangle is width times height times 1/2. So the width is 2, the height is 2. So 1/2 times 2 times 2. Plus, and then this side, the right side here, it is going to still be a triangle. So it's going to be 1/2 times a width of 3 times a height of 3. When we get into the fundamental theorem of calculus for calculating these instead of just the area, so where we would use the antiderivative, splitting it up would make even more sense. So overall, you're going to get 2 plus 9/2, which is equal to, let's see here, I think that's going to be 6.5. So 6.5. So yeah, this is why that might be useful. Let's look at the last two properties of definite integrals. So the last two properties are related. So they are kind of these comparison properties. So first, if you have that f of x is less than or equal to g of x on an entire interval from a to b, so for all of those x, then the integral of f of x from a to b is going to be less than or equal to the integral from a to b of g of x dx. So let's zoom on in and see kind of a drawing of this. So for an example, we're going to go here and make that skinnier. Okay, so for example, let's say that we're looking at a drawing, and you have a to b, and you have some f of x, and you have some g of x. Now, what's important here is that g of x is greater than f of x specifically on the interval from a to b. We don't care about anything to the left of a or to the right of b. And so if we're looking at this, it's pretty obvious to tell that the area under f of x is definitely less than the area under g of x, which is just the whole idea. If f of x is less than or equal to g of x, which here at a it's equal to, then the area is going to be less than or equal to g of x. So yeah, just that's your example for number 7. Now let's look at number 8. This one's a little bit more useful. Actually, they're both pretty useful if you're dealing with functions that are not super simple. So a lot of times we've been dealing with things that are polynomials, maybe rational, but you can get really weird functions in the real world. And so instead of knowing the exact amount or being able to calculate an area, you might just want to bound an area. So here, if we have, as an example, I want to go to black. So if we have as an example, if we look at this, let's say you have a function from a to b where you have f of x is in here, and it is bound between a and b between 8 and 6. So between 8 and 6, it is bounded. Then, if we were to look at this area, then the area under the curve is definitely less than this rectangle right here, which has an area of 6 times b minus a, right? So we know that the area under the curve is more than this rectangle. However, we also know it is less than the larger rectangle. It is less than the larger rectangle, which is 8 times b minus a. And so we get that here, let's say that a is 1 and b is 4. Okay, b is 4. Then we would have that the integral of f of x dx from 1 to 4 is going to be greater than 6 times 3, which is 4 minus 1, but less than 8 times 3. And so 6 times 3 is 18, 8 times 3 is 24, and so that gives us a pretty narrow idea of what that area would be. This would also be useful if, let's say, before you even start a problem, if you had it graphed, you can be like, well, I know that it's going to be between these two values. Then when you actually calculate the area, especially if you were using like the Riemann sum definition of the integral, you could be like, oh, I ended up between these two values, so that's a good thing. Or you can get something not between those two values. You can be like, something went wrong. Let me go see if I can find what that was. So then I want to semi-end today's discussion with a you-do problem. And then I want to go over one of the problems from your quiz, because I think that a lot of people have struggled with it. So for the you-do, if the integral from 1 to 6 f of x dx is equal to 7, the integral from 4 to 6 g of x dx is equal to 2, and the integral from 4 to 6 of f of x minus g of x dx is equal to 9, what is the integral from 1 to 4 of 12 f of x plus 3 dx? So you're going to need to use many of the different types of properties from today in order to solve this. Again, I'm not giving you an exact what f of x or g of x are. I just want you to use these properties to solve this. This is very similar to problems that have been on exams in the past, especially in like the multiple choice. So go through, see if you can do this. And now let's look at that problem 4 from quiz. So problem 4 from the quiz. And so this was an optimization problem, and you had a triangle where the bottom was length B, this side was length A, and then the height was H. And you were asked, optimize, and then you had theta. Optimize the area of the triangle. So the area of the triangle, real easy, is going to be 1/2 base times height. But then we also get that we're optimizing by adjusting theta. So the easy thing here to do is to say that sine of theta is going to be h over a, because sine is opposite over hypotenuse. And so h is going to be equal to a sine of theta. So if we go back to our area equation, we're going to have 1/2 b times a sine of theta. So this is what you would take the derivative of. And when you do that, remember a and b are constants. And so 1/2 ba stays there. And then the derivative of sine of theta is cosine of theta. And so this right here is what you would set equal to 0 and then solve for theta. And so you should end up with theta is equal to pi over 2 eventually when you go through and do it. And then you would also need to do the check with either the first or the second derivative in order to get full credit. If you did the partial credit, I forget what was the equation you had to do it. You just had to take the derivative, set it equal to 0, solve, and then do the check to get that partial credit. And then also for number 3, so problem 3 of the quiz. So problem 3 of the quiz, you had to look at the related rates of this theta and then the slope. And so real quick, the slope is going to be your vertical, your height, over your width, right? Because slope is rise over run. It's also h over w is equal to tangent of theta because it's opposite over adjacent. And so you can have tangent of theta is equal to your slope m, right? And so when you take the derivative of this with respect to time, the derivative of tangent of theta is secant squared of theta times d theta dt. And then the derivative of your slope is just the derivative of your slope with respect to time, which is dm dt. And so you had a value for d theta dt. It was either like pi over 19 or pi over 21. And then you needed to check for theta at pi over 6. And then plug that in to find how your slope was changing. And so that was how you should have approached problem 3 on the quiz. So the last thing I want to say is that you should have paper homework posted by tomorrow evening. Today I will be working on grading your quizzes, as well as today there will be a Zoom meeting from 3:30 to 4 p.m. So be looking for that. I will be posting that in the announcements. If you have questions about the quiz or about how to do the you-do problem, please show up to the Zoom meeting today. So that's it, and I will be posting again tomorrow. Bye, guys.